Hey guys, today we were looking at 8.2 set of notes, which is all about just basic graphing of a quadratic. We talked about yesterday, or I guess in the last section, 8.1 was all about describing those key characteristics of parabolas with the vertex, the AOS, and then obviously some domain and range, intervals of increasing and decreasing. But for graphing specifically, because we have that AOS, what we really are focusing on is finding where our vertex happens, and then we'll develop both some shortcuts on how we can actually graph those parabolas without having to find a bunch of points. Because like we've done in the past, if we don't know what a graph looks like or how to graph it using shortcuts or other different specific methods, we just pick out some x values, plug them in, and get y values back out, and we plot those points. So we know the general shape of what a quadratic looks like. We know, obviously, we spent time describing them in 8.1. But if I wanted to just graph the very basic, easiest parabola that is possible, y equals x squared. If I didn't know where to put my points, I would just pick out x values, plug them in, and I would get y values back out. So usually when we do this, and if you remember back in exponentials, back in chapter 6, when we graphed those exponentials before we figured out the shortcut, we just picked out some different x values. And let's just say we're going to pick out 5 x values to figure out what it looks like. And I'm just going to do from -2 to 2. So that gives me 5 points, some positive, some negative. So if I plug those values in, if I plugged in those x values, -2 squared is 4. -1 squared is 1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. So I have those 3 coordinates. -2 comma 4 is right there on my graph. -1 comma 1, 0, 0, 1, 1, and 2, 4. So that is going to give me that shape of a parabola that we're looking for. So I can go ahead and just connect my dots as best I can. So that is the basic parabola. That's standard parent graph of a parabola. Now, instead of having to go through and do that every single time, what we can do and what exists here is a little bit of a shortcut method on how we can graph our parabola once we know where the vertex is. Moving forward, the next couple of sections that we'll do are going to be different forms of how an equation can be written. We'll do standard form, intercepts form, vertex form, a bunch of different ways an equation can be written. But all of them differ just in how we find my vertex. As we described yesterday with those key characteristics, the vertex is the most important thing. If we know where that vertex is, we know where the axis of symmetry is, the AOS. We know, where my domain or my range is based off of. It was always that kind of crucial dividing point for my intervals of increasing and decreasing. It is the most important thing in my parabola. So if I know where that vertex is, then everything else just kind of falls in place. So with these, if I wanted to graph them, once I knew where the vertex happens, which for right now, just a regular parent graph without anything shifting around or anything, it happens at the origin, so at 0, 0. From here, this pattern exists in how I get from one point to the next in my graph. If I look at my vertex to my first point on the right, I go up 1 over 1. And then from that point, I go up 1, 2, 3 over 1. The next point, which I happen to go through nicely, which is awesome for me. My next point, if I plugged in 3, I'd get 9. So this next point is up 5 over 1. So you can see my vertical changes. I'm going up by my odd numbers, and then I'm just going over 1 to get my shape. So we call this the shortcut the 1, 3, 5 shortcut. Because getting from one point to the next in my parabola, I go up 1 over 1, up 3 over 1, up 5 over 1. And that's always the case for a parabola. Now, obviously, we'll look at how some different things are going to be adjusting that, things that will change my vertical changes. But if I don't have any kind of stretch or shrink happening, if I don't make it any taller or smaller than how it usually is, then I follow that 1, 3, 5 shortcut. And most of them that we'll do moving forward will just be an x squared for my equation. So we'll be able to follow that 1, 3, 5 shortcut. Now today is the exception to that rule because today we're focused on not moving my vertex around. We're focused on just having, just a basic quadratic with just maybe some stretching, shrinking, or reflecting. But that's my shortcut to get from one to the next. So if I wanted to, again, without having graphed it already, my regular graph started at 0, 0. That's my parent graph's vertex. So I can go up 1 over 1, up 1, 2, 3 over 1, up 1, 2, 3, 4, 5 over 1. So I've got those 3 points on the right. Because we know that my axis of symmetry, my AOS, is always a vertical line that goes through my vertex, I also have up 1 over 1, up 3 over 1, up 5 over 1 on the other side of my graph as well. So that gives us that kind of scoop, that curved shape that is my graph. And then just connect your dots. Okay. So some ways that we can adjust that 1, 3, 5 shortcut is, if you remember back in middle school, and this is something we'll revisit again in Algebra 2. I'm pretty sure you guys do this next year in geometry. I know we did it in pre-algebra for what I'm teaching now, so you should have done it last year, or maybe you're currently doing it if you're one who's doubled up, was transformations. Transformations of graphs with translating up, down, left, and right, stretching and shrinking, doing some reflections, just changing kind of the shape and the location of my graph based on some set rules. With these, we're going to be focused on stretching and shrinking. So in this case, I've got a 1/2 out in front of my graph, or out in front of my x squared term. So you could, if you wanted to, still just pick out some x values, plug them in, and then plot those points. But if we wanted to use my shortcut, I'm going to still start with my vertex and my AOS. So I haven't shifted around at all. My vertex still happens at 0, 0. My axis of symmetry, my AOS, is the vertical line through that point. Now my 1, 3, 5 shortcut in this case has to be adjusted because that 1, 3, and 5, those were my vertical changes, right? 1, 3, 5 shortcut tells me I go up 1 over 1, up 3 over 1, up 5 over 1. Now what these multipliers out in front do are changing how tall my graph is. So I'm going to take that 1/2 and multiply it, not 1/3, 1/2, multiply it by my vertical change. So I'm going to take half of those amounts. So instead of going up 1, 3, and 5, we're going to go up 1/2, up 1.5, and then up 2.5, because that's half of 1, half of 3, and half of 5. So on my graph, I'm going to go up 1/2 and over 1, up 1.5 over 1, up 2.5 and over 1. We'll do that on the same side. Or I do the same thing on the other side. Up 1/2 over 1, up 1.5 over 1, up 2.5 and over 1. And I'll just connect my graph, connect my points. Now my rule moving forward, I require 5 points on your parabola. You should have your vertex, 2 points on the left, 2 points on the right. So here I did 7 points. I did my vertex 3 on the left, 3 on the right. You're only required to do 2 on the left, 2 on the right, besides vertex. Okay. Next one, box 3, adding a reflection in here. So I can, if you don't want to keep track of these rules, you're not going to be asked to describe the transformations. You're not going to be asked to, tell me whether it was a stretch or a shrink or a reflection or any of that stuff. Moving forward, you're going to be dealing with just some graphs that might have these numbers as their A values. If you remember from that standard form of what a quadratic looks like when we were going through and doing our solving and stuff. If we had a leading coefficient of a number, it made our graph a little bit more, or it made our factoring a little bit more difficult last chapter. Here, this is just how we're going to be able to handle what those A values are going to do for our graphs. So in the case of box number 3, I've got a negative out in front of my x squared along with a 2. So that's going to do 2 different things for my graph. My negative is going to cause it to be reflected, which means instead of a happy face for my parabola, it's going to be a frowny face. So it's going to be opening down instead of opening up. That 2 that's there is also going to be stretching my graph out, so it's taller than it usually is. So instead of 1, 3, 5, it'll be 2, 6, 10. So if you don't want to remember those rules, again, all we have to do is take my 1, 3, 5 shortcut and multiply it by whatever this a value is, whatever number is attached to my x squared. So I have to multiply 1 times negative 2, 3 times negative 2, and then 5 times negative 2. So negative 2 times 1 is negative 2, 3 times negative 2 is negative 6, and then 5 times negative 2 is negative 10. So I'm still going to start with my vertex at the origin, because we haven't shifted around at all. That's how I start all my problems until we hit box 4, which we'll see in a second. But we've got that as my graph that's set up. I've got the vertex and the AOS labeled. So now, instead of going up 1 over 1, up 3 over 1, up 5 over 1, I follow these new numbers. So now I go down 2 over 1. Whoops, I want that to be blue. So down 2 over 1 on both sides. Down 1, 2, 3, 4, 5, 6 over 1 on both sides. And that's all it's going to be able to fit, which is totally fine because that's at 5 points already. I've got, the vertex, 2 on the left, 2 on the right. So that is what my graph is looking like. There we go. So that is the shape of my parabola for box number 3. And again, we can see it's taller than a normal parabola. It's more narrow. It's more slender, but it also is opening down instead of opening up because of that negative sign. Okay. So the one exception to our rule, which I don't remember off the top of my head whether you have one of these on the homework. This will be more so, we'll be able to handle these using different skills moving forward once we look at the different forms an equation can take on. But as soon as you have anything that's added or subtracted in my equation, all that does is move my vertex up and down. So if I have in this case, I have a plus 3 in my graph or in my equation, all that's going to do is take my vertex from 0, 0 up 3 units. So from the vertex, I can go up 3, and from the origin, I can go up 3, and there's my vertex. So right there at 0, 3 is now my vertex. I don't have an a value. Well, really, I don't see an a value. My a value is 1 here. So I get to follow just the regular 1, 3, 5 shortcut. So before I forget, I'll go ahead and throw my AOS here, vertical dotted line. And then from my vertex, up 1 over 1 on both sides, up 1, 2, 3 over 1. And I can't go to the 5th one, it's off my graph. But again, totally fine because I already have 5 points on my graph. I can go connect the dots, connect the dots. There we go. All right. So there is my last graph. Again, the big takeaway here is the 1, 3, 5 shortcut. All of this other stuff is kind of weird. It's kind of different. It's more so just focusing on how we can graph the rest of my parabola once we know where the vertex is. Because again, the next couple of sections moving forward are going to be looking at different forms that my equation can take on, different ways that my quadratic can be written, and we have different skills and formulas and stuff for how we can find the vertex for that particular equation. What we need to walk away with today is being able to graph once I know where the vertex is. So just following that 1, 3, 5 shortcut, or if I have something out in front of my x squared, like I did in boxes 2 and 3, then I just multiplied that number times 1, 3, 5 to adjust those heights. So your homework that you guys will be working on next is on page 429, 3 through 12 all. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.